Dylan, what are the two types of charge? Good. Positive and negative. Jordan, what does positive charge result from? Where does it come from? Protons, yeah, but it's not just necessarily protons. If you have a positively charged object, you've got protons and electrons, but you must have more protons than electrons. Good. If you have a negatively charged object, then you've got to have more electrons than protons. Make sense? Good. Good. Where do the protons exist, Jordan? You just kind of told me this already. Right, the protons exist in the nucleus. What else exists in the nucleus? The neutrons, which are pretty much irrelevant for us in this unit because they have no electric charge. Surrounding the nucleus will be the electrons orbiting around the nucleus. What's the symbol for electric charge? We want to measure the amount of charge you have. If we measure the amount of speed we'd have, we'd say V is equal to something, meters per second. What do we say when we're measuring charge? Q, right. The electric charge is measured using the symbol Q, and the units for charge would be what? C, it's a coulomb, capital C, or coulombs, named after a guy named Charles Augustin de Coulomb. What's the charge of an electron? Does anybody know that? If you don't, you can look it up. Find it on your data sheet. It says negative 1e, it says. What does that E mean? E is the, not the electrons per se. No. E is the elementary charge. What's the value of the elementary charge? Good. So that means that the charge of an electron is 1 times that, or negative 1.6 times 10 to the minus 19 coulombs. The charge of a proton is plus 1e. Plus 1e means that the charge of the proton is 1.6, positive 1.6 times 10 to the minus 19 coulombs. Not a coincidence that those two charges are the same. They must be balanced. Okay, if we have a carbon atom, we have 6 protons, we have 6 electrons. That makes the total charge of a carbon atom what? 0, right? Makes it 0. If we have sodium, a sodium ion has, how many protons does sodium have? Anybody know? Sodium ion is plus 1. Looks like this. Not sure how many protons it has off the top of my head. But it's a charge of plus 1. Plus 1 elementary charge. That means regardless of how many protons it has, we know that it has how many electrons? Not 1. No. 1 less electron than proton. It's got 1 extra proton. If we have chlorine, then regardless of how many protons we have, we know we have how many electrons? 1 more. 1 more electron than we have protons. Good. What are the 3 laws of electric charge? Okay. Good. Opposite charges attract each other, so that means that positive attracts negative, negative attracts positive. What's the second law of electric charge? Good. Charges that are the same, positive repels positive, negative repels negative. Like charges repel each other. And the third one is? Good. Charged objects attract neutral objects. Yesterday you kind of just had to trust me on that. Today you're going to learn why charged objects attract neutral objects. What's a conductor? Give an example of a good conductor, an electrical conductor, not a heat conductor, an electrical conductor. Aluminum is a good example. Pretty much any metal is a good example of a conductor. What's different about metals versus nonmetals? Has to do with the electrons. Michael? Well, yeah, well, not exactly more space, but the electrons are more free to move around. It's easier for the electrons to leave the orbit of the nucleus and to move around. So they can be transferred from one place to the other quite easily, okay? So a conductor is a material in which the electrons on the outermost levels are a little bit more free to move around. An insulator, on the other hand, is a material in which the electrons on the outermost levels aren't free to move around, at least not as much. Insulator, is that spelled right? Insulator, yeah. They're not as free to move around as they are on the conductor. Does that make sense? There's varying degrees of conductivity, so that doesn't mean that copper has the same conductivity. It doesn't mean that it's the same quality of a conductor as, say, gold is, or silver is, or carbon is, but they're all conductors. Wood, on the other hand, is a pretty good insulator. It's a poor conductor, but it doesn't mean that it prevents the flow of electricity exactly the same as plastic or glass does. There's varying degrees of conductors and insulators. Tell me what the law of conservation of energy tells us. Energy can't be created or destroyed. Law of conservation of mass? Mass can't be created or destroyed. The law of conservation of charge? Charge can't be created or destroyed. It can be transferred from one thing to the other, but it can't be created and it can't be destroyed. If something's going to be transferred, what's it going to be? Is it going to be the positives? Is it going to be the negatives? Negatives. Right. Why is it the negatives, the electrons, that are transferred as opposed to the positives, the protons? Good. The electrons are moving around the nucleus, and they're attracted to the nucleus. They want to stay there, but they also have a little bit more opportunity to leave. It doesn't take as much energy to cause them to leave as it would the protons. Those protons are held in place pretty strongly by this force that we call the strong nuclear force. And it's strong over very short distances. So that nucleus is pretty well tied together, pretty tightly tied together. Electrons, not so much so. Just requires a little bit of energy to get those things to leave. All right, good. Yesterday, we did an example where we had 3 charges. We were touching things together, and we wanted to see what the final charge was on each of these. I'm going to give you one of those examples that we're going to do as a group here right now, and then I'll give you another example that you're going to do by yourself, which came from an old diploma exam a number of years ago. So let's just take a look up here. We've got plus 5 coulombs, we've got negative 2 coulombs, and we've got negative 6 coulombs. We're going to say 1 touches 2. Then we're going to say 2 touches 3. What's the final charge on all 3 of those as a result of those 2 events taking place? 1 touching 2, then 2 touching 3. First thing we want to do is specifically look at charge 1 and charge 2. Plus 5 and minus 2. What is the total charge between those 2 objects? Plus 3. If we take plus 3 as a total charge and divvy it up among those 2 charges, which is exactly what we do here. Touch 2 objects together, they split up the charge. They even out the charge. Plus 3 is evened out as what and what? Good. Plus 3 is evened out as 1.5 and 1.5. Positive 1.5, positive 1.5 coulombs. The third one is still going to be minus 6 because we haven't done anything with it yet. Now we're going to take a look at charge 2 and charge 3. 1.5 and negative 6. We add those up. We get a total charge between charge 2 and charge 3 of negative 4.5. If we even that out among 2 different charges, what's it going to be for each of those? Total charge between the 2 of them of negative 4.5. It's going to even out to be negative 2.25 and negative 2.25. The first charge is going to remain as positive 1.5 coulombs. So after these 2 events have taken place, the first charge is going to be 1.5 coulombs. The second one, 2.25, negative 2.25. And the third one is going to be negative 2.25 coulombs. We're good? Let's just do a little check on that, just to make sure. Let's add up all the charges after each event takes place. Plus 5, negative 2, negative 6 gives me what? Negative 3? Is that right? Yeah, negative 3 coulombs is the total charge here. What's the total charge in the middle one? 1.5, 1.5, negative 6 gives me negative 3. 1.5, negative 2.25, negative 2.25 gives me negative 3 coulombs. Should all 3 of those be the same? What law tells us that all 3 of those need to be the same? Conservation of charge. Charge can't be created or destroyed. It can be moved from one to the other, but it can't be created and destroyed. Let's take a quick look at that first one again. 5 and negative 2 balanced out. Which way did the charge go? Did it go from the 5 to the 2, or did it go from the 2 to the 5? How do you know that, Dylan? Good. The 2 is a negative charge. It has more electrons. What is it that's going to transfer, electrons or protons? If electrons transfer, then it's going to be the one that has more electrons that loses electrons. In other words, the negative 2 is going to transfer electrons to the plus 5. Okay? It's good? All right. Everybody take a look at this question, please, which is a multiple choice question that appeared on the diploma exam about 11 or 12 years ago. This is also in the multiple choice booklet that you have in your Unit 2 worksheet booklet. All right, you've had a chance to work on it. Let's take a look at it. Two conducting spheres have identical surface areas. Sphere A has a charge of 4.5 microcoulombs. B is negative 2.4 microcoulombs. A microcoulomb, by the way, is 10 to the minus 6. Now, that doesn't really matter for us at this question because we don't have to convert here. All we're doing is averaging these two together. It doesn't matter whether we do it in coulombs or microcoulombs. But we need to be familiar with that conversion because there are times when we need to be in coulombs. I told you guys yesterday that a coulomb is a really, really big unit of charge, right? So we often don't measure it in coulombs. We often measure it in microcoulombs or nanocoulombs or millicoulombs. Here we're in microcoulombs. We also have a negative there. It's probably not a bad idea to circle that as well, just to remind us that it's not just two positive charges. They touch each other. We want to find out what the charge on sphere A is after they touch each other. We've got 4.5 microcoulombs. We've got negative 2.4 microcoulombs. We add those up, and we're going to end up getting 2.10 microcoulombs. Is that the right answer? How many people said B? If you didn't say B, what did you do? Good. Divide by 2. That's the total charge that we have on both of them combined. We want the charge on each one of them. So divide that by 2 becomes 1.05 microcoulombs. The answer is A for that. I'd like you also to take a look at this multiple choice question, 33. This one's a little bit different. This one you're going to have to kind of think a little bit about. We'll spend some time going over this when you're done, but I want to see what you can do with it first before I give you any hints for it. Okay, so take 30 seconds, 45 seconds, see what you can do, then we'll take a look at it. All right, in order to help you to understand this, for those of you who are struggling through this a little bit, I want to do a little analogy here, okay? I'm going to draw a picture here of a bag of apples. I'm not going to tell you how many apples are in that bag, but I am going to tell you that the mass of that bag of apples is 600 grams. We can assume that the bag doesn't have any mass. The bag itself is massless, but that there are a number of apples inside, total weighing 600 grams. Over here on this side, I'm going to draw a picture of an apple. That apple, that one apple, is going to have a mass of 100 grams. My question, and I think it's a pretty easy one, my question is how many apples are in that bag? 6. How do you know? How did you figure that out? To find the number of apples, intuitively, you divide it, the total mass, the 600 gram mass of the bag, divide it by the mass of one apple. That's the 100 gram apple. 600 grams divided by 100 grams is equal to 6. Therefore, there must be 6 apples inside that bag. Does that make sense? Okay, that's an example I think that everybody can understand. Okay, we've done that before. If I ask my 10-year-old son, there's 600 grams in this bag, there's 100 gram apple, he'd be able to do that. Okay, 10-year-olds can do that. Well, 33 is not really much different. It's just dealing with a quantity that we're not familiar with, that is charge, and we're dealing with numbers that are a little bit more awkward than 600 and 100. Here's my bag of electrons. My bag of electrons has a charge of negative 3.6 times 10 to the minus 17. Over here we have an electron that for whatever reason has a little stem popping out of it. That electron has a charge of negative 1.60 times 10 to the minus 19 coulombs. How am I going to find the number of electrons? Well, it's not the total mass divided by the mass of 1. Although if I had the total mass, I could do that. I've got the total charge. So we're going to say total mass, total charge, divided by the charge for one electron. When we do that division, we should end up getting 225, I believe. Now, they want that expressed A in scientific notation, so let's do that, 2.25 times 10 to the 2. And then secondly, they want that expressed as A decimal BC times 10 to the D. They want the value of A, B, C, and D. How do we write that? A is 2, B is 2, C is 5, and D is 2. So my answer would be 2, 2, 5, 2 on an exam. Now, they could also ask me to express that one as B times 10 to the W. What's the value of B? How do we express that one? It would be 2.25. B can be a decimal number. Okay, if you're looking for those individual digits, then we're looking only for the numbers themselves. If we're looking for B, the entire base, then we're looking for that number along with any decimal places it would be there. Today we're going to talk about how we get a charge on object. We've talked to this point about charges on objects, positive and negative, and the fact that we have more electrons and protons, or more protons and electrons, or whatever. But how do we get those electrons from one place to the other? How do we charge the objects? There's two ways of charging objects. Charging by conduction, charging by induction. Charging by conduction never involves a transfer of charge. Sorry. That's wrong. Don't write that down. Charging by conduction always involves a charge transfer. So we've always got charges going from one object to another if we have conduction, versus induction, which never involves a transfer of charge. How do you charge an object without moving charges from one thing to the other? We'll talk about that, okay? Talk about it in a minute here. It never involves a charge transfer. Charging by conduction always, or usually at least, usually involves touching. Touch two objects together, charge transfers from one to the other. That's conduction. Rub two objects together, charges transfer, that's conduction. It usually involves touching, but there are scenarios where it doesn't actually have to physically touch, just close enough for charges to arc. If I was to put my hand near the static ball that we used yesterday, and the electrons arced from the static ball to my hand, that would still be conduction, even though my hand wasn't actually touching the dome. Induction never involves touching. Now let's break the conduction down into two subcategories, friction and charging by contact. Charging by friction involves rubbing two things together. For instance, rabbit fur and a piece of plastic that I have up here. If I rub the rabbit fur against the plastic, then both of them will gain a charge. Electrons are being transferred from the rabbit fur to the plastic, making the plastic negative and making the rabbit fur positive. They've both become charged object. What do you do with your dead rabbits? What do you do with your dead rabbits? Make rabbit fur. You make rabbit fur. Get rabbits run up my street all the time. Every time I turn around, there's rabbits running up my street. If I bring this a little bit, it's attracting the hair a little bit. Okay, that tells us there's a little bit of charge on this plastic tube here. Okay, and that happened because of charging by friction. Okay, if I rubbed the rabbit fur against this, it charged by friction. Walk across carpet, that's charging by friction, right? Rubbing your feet against the carpet, charging by friction. I think it was Jared that maybe asked me the other day about the trampoline, was it? Is that you? No, maybe it was another class even. You jump on a trampoline, what happens sometimes to your hair? It gets all frizzy and stands up sometimes, right? Depends on the type of hair that you have. That's charging by friction. As your feet, your sock feet, rub against the trampoline, electrons transfer from the trampoline to your hair, charging by friction. Versus charging by contact, which simply involves touching or almost touching two things together. I'll put the word touching in quotation marks, because there are times when they don't actually have to touch. I have a charge of 0. You have a charge of -2. You walk over and touch me on the finger. What happens? I get a shock. I get a shock because electrons were just transferred from you to me. That was charging by contact. Even if, when you walk over and you go to touch me, the charges discharge or arc from you to me before we actually make contact. If the charge transfers because you're bringing your finger close, we still call it charging by contact, even if it doesn't actually physically make contact. Now, sometimes, because that word can be a little bit misleading sometimes we don't even bother calling it by its subcategory name. We just call it charging by conduction. We just use that umbrella term, conduction, to describe charging by contact. Let's take a look at induction now, which never involves a charge transfer and never involves touching. We got a neutral object here. We got 3 positives and we got 3 negatives. We're going to bring another negative object nearby. A whole bunch of negative excess charges on there. What happens when I bring that negatively charged object nearby? First of all, what happens to the protons in the neutral object? Where are they going to go? Where? Good. Jared, this is the first class all day that's answered that question correctly the first time. The protons go nowhere. They stay exactly where they are. Protons don't move, right? If anything moves, it's going to be electrons. So the protons stay where they are. But the electrons do go somewhere. Where do those 3 electrons go? Are they attracted to this negative rod or repelled by this negative rod? Negatives are going to be repelled by the negative rod. So what do I have here? On the left-hand side of this object, I've got a negative charge. On the right-hand side, I've got a positive charge. The overall charge of this object is still neutral, but I've got a separation of charge. It's neutral, but it's separated. Let's draw another neutral object here. Let's this time bring a positive object nearby. What happens to the protons here, Jared? Nothing, they stay where they are. What happens to the electrons? This time they're going to be attracted, right? The electrons are attracted to the right-hand side. So now we've still got a neutral object, but now we've got a separation of charge, where the left side is now positive and the right side is now negative. Now there's a couple things that I want you to notice from this. Number one, these 2 neutral objects are still neutral objects. It's just that the charge is separated, one side and the other side. But overall, it's still neutral. The second thing that I want you to notice is that the side that's closest to the charging object is always opposite charge to the charging object. Right, Justina? Look up here. This one is positive. This object is negative. This side is negative. This object is positive. That's really important, because that comes back to that third law of electrostatics, which says charged objects attract neutral objects. When you bring this negative rod nearby this neutral object, you induce a temporary separation of charge. It's temporary because if I take that away, it's going to go back to where it was before. But it causes the force of attraction between that charged object and that neutral object, because the side of the object that is nearest the charging rod is always going to be opposite, and opposites attract. So this negative rod attracts this positive side of this neutral object. This positive rod attracts the negative side of this neutral object. Charged objects attract neutral objects because of an induced temporary separation of charge. How do we make it permanent? How do we make it so that when I take this away or this away, it doesn't go back to the way it was before? I'm going to redraw this so I have a little bit more space here. Here's my neutral object. Here's my negative object. Bring that negative object nearby. What happens to the positives? Jared, what happens to the positives? Good. What happens to the negatives, somebody? They're going to get pushed over to the left-hand side. It's exactly what I had drawn in the last diagram to this point. But now what I'm going to do is attach what we call a ground wire. A ground wire is a physical connection. It doesn't have to be physically a wire, but it has to be a conductor from the object to the Earth. The Earth provides us with an infinite sink of electrons. We can put as many electrons as we want down there. It doesn't affect it. Okay, the analogy that I gave earlier today to somebody when they were questioning me on this was swimming in a lake. Okay? My son and I and my brother-in-law, sister-in-law, and their kids, my wife, we're all swimming in a place called Maple Lake in BC a couple of years ago. My brother-in-law and sister-in-law have a boat. We're out in the middle of the lake, which is a couple hundred meters deep. It's a massive lake. We're swimming off this boat. My son says, I gotta pee. I have to pee. We're out in the middle of a lake. Where's he going to pee? My brother-in-law says, just pee in the lake. He's like, no, I can't pee in the lake. It's gonna mess up the lake. He says, well, it's not going to mess up the lake. It's going to be fine. The lake is huge. It's not going to affect anything. And he's right, it's not. So you pee in the lake. It doesn't make any difference in the world because there's so much water in there that a little bit of pee in the lake isn't going to make any difference in the world. The Earth is so big that if we send a bunch of extra electrons to the left-hand side of this object and we allow them to keep going down into the ground, then it doesn't really affect the Earth at all because the Earth is so big. So you got a bunch of electrons, enough electrons to maybe electrocute you if you actually touch this object. It's not going to affect the Earth because the Earth is so massive. Does that make sense? What happens when I take this thing away, though? They're going to go right back where they came from. It's not permanent yet. How do I make it permanent? Take off the wire. Cut the ground wire. If you cut that ground wire, the electrons have no way of coming back now. Even after you take this thing away, the electrons have to stay in the ground. Now we're left with a permanently positively charged object. We can do the same thing with something that's a positively charged object nearby a neutral object. Here's my neutral. Here's my positive. What happens to the positives? Nothing. What happens to the negatives? The negatives get attracted to the right-hand side. Oops, too many. Negatives get attracted to the right-hand side. What do? We attach a ground wire here. The electrons this time don't go down from the object into the ground. Rather, electrons go from the ground into the object. What do we have now? Whole bunch of extra electrons there. What do we do with them? Well, we cut that ground wire, and they're going to stay where they are. Now we've got a permanently negatively charged object. Bring a positive nearby, makes it negative. Bring a negative nearby, it makes it positive. Well, this is great. You can remember this chart, and you can remember these pictures that I've drawn, and these definitions, and all these things that I've told you, but so what? Where's the application to this? Where do we use this in everyday life or in technology or whatever? I'm going to tell you a quick story here first. This isn't so much everyday life. It was for me when I was in university, but for most people this doesn't happen. Then we'll give you a couple technological applications of, where this stuff applies so that you can see that it's not just, a pen and paper kind of thing. Over 20 years ago when I was in university, I went to university in 1990 to a place called St. Francis Xavier in Antigonish, Nova Scotia, a small town of about 6,000 people, and a university of only about 3,000. It was great. You should go there. I lived on campus for 2 years, which I would highly recommend to everybody, no matter where you decide to go. Live on campus for a while. But then I moved off campus with 4 other friends from my residence. One of them was a philosophy student, one of them was a biology student, 2 were music students. So it was kind of a mix. Biology, philosophy, music, and physics. We lived in a dump. The house that we rented was an absolute dump. The floors were so crooked, so slanted, that you could literally put a golf ball in one corner of a room and it would roll quite quickly to another corner of a room. The walls, the wallpaper in the kitchen was probably from the 60s, from the 1960s, which was 30 years before we were ever there, which was ugly, But good in a way, because when we had our spaghetti fights in the kitchen, you couldn't really notice the spaghetti stuck to the wall. So in a way, it was kind of good. Our stairs were about this wide each. So when you'd go to walk up the stairs, sometimes you'd slip and you'd fall down the stairs. You'd get up like pretty much all the stairs, and then you'd all of a sudden slip and dud, all the way down the stairs. Our living room didn't have carpet. Our living room had AstroTurf, which was great for a bunch of guys. You watch a football game or a baseball game, it kind of felt like you were there, almost. Yeah, yeah. Isn't it great? I don't regret living there. I know my parents were mortified that I would ever decide to rent this house, but I was 21 years old, so not much they could do about it. But one of the things that, probably the thing that actually scared me the most, and never really scared me at the time, just kind of scared me after the fact, was the wiring in the house. One day, myself and 3 of my friends are sitting around the table in the kitchen. Over here is the stove. Over here is the refrigerator. And the porch, or the porch is out here, where the front door, the side door that we would come into the house is right there. So when you come into the house, you'd have to walk through here in between the fridge and the stove. The fridge and the stove are pretty close together. 4 of us sitting around the table, 1 of us standing right here at the stove, this gas stove, cooking supper. Okay, so he's got a frying pan, he's doing something with the frying pan, flipping something, moving it around, whatever. He reaches over, grabs something out of the fridge, gets a shock, gets an electric shock. And he says, I just got an electric shock, I just got a shock. And it's only 1 shock, nobody's really too concerned about it. But then he does it again at some point, gets another shock, and he does it again and gets another shock. And we're starting to become a little bit like, what's going on? Why does he keep getting this shock? So he starts feeling around, touching all these different spots and seeing where he's getting the shock from. Can't find it. Then he realizes, almost by accident, that if he touches the fridge and the stove at the same time, that's when he gets the shock. So he tells us that. And then he realizes that if he touches the fridge and the stove for more than just a brief second, the shock actually lasts as long as he holds on. So if you can hold on for 1 or 2 seconds, the shock will last for 1 or 2 seconds. So now, you can imagine if this was 5 girls in this kitchen right now, 5 girls who would probably be somewhat more intelligent than the 5 guys were, they would probably call an electrician at this point and say, there's something wrong. 5 guys sitting around a table in the kitchen say, let me try. Let me try, and who can hold on the longest? Exactly. So then it kind of became a game where we'd go and touch it. It was difficult at first because like the shock was pretty intense. You touch it and your hands would go away from it right away. But as you became kind of accustomed to it or desensitized to it, you got to be able to do it for quite a long time. We got to be able to do it at time, you know, after a while, after a couple of weeks, for probably a minute at a time.
Like really bad for you?
Probably. Yeah, probably was. Probably wasn't. We're all still alive, so couldn't have been too bad for us, right? It got to the point actually where, like, we had some pretty serious competitions going. Like, sometimes you'd wake up in the morning, if you had a late class, like an 11 o'clock class was your first class, sometimes you'd come downstairs, and on the fridge would be a piece of paper taped to the fridge that had a guy's name and then a time, like 46 seconds, or 48 seconds. That told you that, hey, I just set the record this morning. So then what would you do? 46 seconds, I can beat that. So then you'd stand there all by yourself and try to beat 46 seconds, or whatever it was. My roommates were biology students, philosophy students, music students. I was the physics student, so of course it always came down to me to try to explain things like this. And at first, I had no idea why this was doing this. And then it occurred to me one day why this was doing this. Our house wasn't grounded. The wiring at our house was circa 19-something, right? When electricity started flowing in houses, probably. It was ridiculous. Our plugins were 2-prong plugins. That third grounding prong wasn't there. If we had to plug something in, like a computer that had 3 prongs, then we had to either break the prong off, the 3rd prong off, or if it was something like a computer, we didn't want to do that, obviously, so you'd buy a cheap extension cord, break the 3rd prong off of the extension cord, plug it in, and then plug your computer into that. Wasn't good. I can't understand how that house never burned down, because it wasn't grounded. And it wasn't good for the computers and whatever we had plugged in either, because it wasn't grounded. They're supposed to be grounded. But in the end, nobody ever died. At least not while we were there anyways. So here's what happened. The fridge has moving parts. Moving parts rub against each other, even against air. Fans rub against air. There's a buildup of electric charge due to charging by conduction. It's charging by friction, right? Rub 2 things together, you transfer charge from one to the other. It's like rubbing a balloon against your hair. The balloon becomes charged so that you can stick it against the wall. The fridge becomes charged when moving parts rub against each other. But if it's not grounded, there's nowhere for that charge to go. So it stays there. It builds up on the fridge. Now, why didn't we notice it earlier? Because when you go up to the fridge on the wooden floor in the kitchen, open the fridge door, you're insulated from the ground. We weren't grounded. But as soon as we touched the fridge in the stove that was connected to the ground by a gas pipe, we were all of a sudden grounding the refrigerator. So we were basically the grounding wire. We touched the fridge, connected to the metal stove, which is connected to the metal pipe that goes down into the ground that carries the gas into the stove, providing a path for electrons to flow from the fridge into the ground. We felt it because the electrons were being transferred through us. It was the electric current flowing through us. I can't imagine it was the safest thing to have that much electric current flowing through us. But I can't imagine it was the safest thing to have that much electric current flowing through the gas pipe either. But in the end, nothing bad ever happened except a couple of good stories. Do it? Yes? Well, we rented the house. We rented the house, and we never told anybody ever about it, no. We told lots of people about it that we knew at the time, because sometimes we'd have people have people over to the house, and it's like, you know, you tell them about it, and it's like, really? So then they'd try it. See, we always kicked their butts, though, because we were used to it, right? They'd hold on to it for 1 second at a time. We'd hold on to it for 45 seconds at a time and make them look like nothing. I'm not so sure this is an everyday application, because not very many people in this world get to hold on to their fridge and stove and electrocute themselves for 45 seconds or 60 seconds at a time. But it is something that you can see is an application, albeit not necessarily every day application, but still an application of what we've just been talking about, right? Charging by friction, grounding wires, and so on and so on and so on. I'm going to give you a couple more examples that probably are a little bit more every day. This is what we call an electrostatic precipitator. This is an air filter. A couple weeks ago, it was really sunny outside my house. I look at, I've got the blinds open in the back, 2 big windows in the back of my house, letting all this bright sunlight come in, and it's really nice in the living room. I'm sitting on the couch, and I look through this beam of sunlight, and you see all this dust floating around, and it's ridiculous. Like, you don't think of all that dust being in your house until you get this really, really bright beam of sunlight that comes in, and you can actually see this dust. It's disgusting, actually. Think you're breathing this in all the time. Electrostatic precipitators help to take that dust out of the air. How does it work? Well, these wavy arrows that you see right here represent the air going into this electrostatic precipitator. This air contains dust, and those little circles are the dust particles. These green ones are the dust particles before they enter. These blue ones are the dust particles partway through. The green dust particles are neutral. Once they encounter these blue negatively charged rods, I'm not sure if you can see the negative there on those blue things or not. They're supposed to be negatively charged. Once these dust particles touch this negatively charged rod, these dust particles become negative. It's charging by conduction. Neutral touches negative. Charging by contact tells us that they're both going to become negative. So now we have not a bunch of neutral dust particles, now we have a bunch of negative dust particles. These negative dust particles then proceed to go through these positively charged metal plates. What happens to these negative dust particles now? That's right. They stick to the plates, right? These negatively charged dust particles are attracted to the positively charged plates. They stick to it. The air goes out the other side, minus the dust particles. Now we get fresh air coming out the other side. You put this in your furnace, you put this anywhere in your house, and it's going to filter out lots of this dust and lots of these impurities. Make sense? Here's another one. Let's say you got a swimming pool in your backyard, and it's a big swimming pool, and you got a big metal fence surrounding that swimming pool, and it's your job to paint that fence. Your dad says, "Okay, Jared, time to paint the fence." Okay, so you say, I don't really want to take a paintbrush and paint that fence. It's going to take me forever. So you say, I'm going to get a spray paint gun. The problem with the spray paint gun is, A, it's going to make a big mess, because you're going to get a lot of overspray going onto the deck of the pool and in the pool itself. B, you're going to waste a lot of paint, right? Because there's going to be a lot of paint that doesn't actually go onto this metal fence. So here's one way to do it. They actually make electrostatic spray guns, electrostatic paint sprayers. In order to make this work, you actually ground the metal fence. Has to be metal, by the way. This doesn't work with a wooden fence. Has to be a conductor. You ground it, and that's easy to do. You literally attach a wire to it, stick that wire into the ground, it's grounded. Provides an opportunity for electrons to go down or to come up, either one. We get a paint gun that is specially designed to have a positively charged rod in here, inside. As this neutral paint goes past this positively charged rod and touches it, what happens to the paint? The paint particles become positive, charging by conduction again, right? Charging by contact specifically. Neutral touches positive, they both become positive. So now we have a bunch of positively charged paint drops coming out. What happens? They're electrostatically attracted to the metal fence. So instead of blowing past the metal fence, they get attracted to the metal fence. Even the paint particles that go past the metal fence, like this, most of them get pulled back in to the metal fence. It's kind of neat, these things, these electrostatic paint sprayers. You can actually spray both sides from the front. The front has pretty much 100% coverage, but even the paint that goes past, right through the fence, gets sucked back in and paints the back. So it covers actually about 80 or 90% of the actual fence by standing in the front spraying it. And you don't get any mess, because almost all of these bubbles of paint, or these molecules of paint, are attracted either to the front or to the back of this metal fence. Again, it only works to the metal fence because it doesn't do any good to ground a wooden fence. Right? Wood's not a conductor. But it works really, really well. That make sense? There's a million other applications that we could see for this as well, a million other applications. And we probably will see some, probably on tests. Probably some that we've never seen before for the first time we see it on a unit test or a diploma exam. Okay, we can handle that. Okay, if I gave you some information about this paint sprayer or about this electrostatic precipitator, you could deal with that. So there's no reason why you can't deal with a new situation that's thrown at you as well. All right? That's it for today. We're not going to continue on any further. We'll continue on with this stuff tomorrow. I know we got a little bit of time left, but we want to end up essentially in the same place as the other classes did, so we'll wrap it up here for today.